Welcome everyone to the December edition of our Liftoff webinar series. Today we are happy to feature Lift member Fidelis to talk a little bit about the shifting role of CAE in an increasingly virtual product development process. My name is Joe Steele, the Communications Director and Legislative Affairs Director here with Lift. Thank you very much for taking the time to join us today. A few housekeeping issues before we do get started. We are recording this session, so if everyone could put their phones or computers on mute, that would be fantastic, so we avoid any background noise. So we are recording this session. As I mentioned, we will be posting this on our website, so folks that were unable to join can view it later, or if folks were interested in sharing it along with their friends or family who think they might be interested in it as well, you can certainly do that. Hope everyone is remaining safe and well as we continue through this pandemic. I know folks are most commonly they're aware of Zoom and aware of all of the different digital platforms that folks are using. So if you do have questions, you can please address them to me, the organizer, Joe Steele, via the chat function that is available on your Zoom taskbar or toolbar, and we can facilitate the Q&A afterwards. I do want to share a few comments about Lift for those who may or may not know who we are and what we do. Lift is one of now 16 National Manufacturing Innovation Institutes. We were stood up in 2014 through the Department of Defense, and we are where manufacturing, technology, and talent matter. We are based in Detroit, and our goal is really to drive American manufacturing into the future through technology and talent development. And we are doing that by connecting the materials, processes, and systems, along with the talent, to drive rapid implementation of smarter manufacturing, because we believe that the next area, the next region, the next country that tackles that first is going to come out ahead on a global scale. So again, we are tackling and solving the manufacturing equation: materials, processes, systems, and talent. We do that really through two of our programs, our main two programs at Lift: Leading Innovations for Tomorrow, which is our technology development program, and Learning Innovations for Tomorrow, which is our talent development program. Both of those together equal what we have here at Lift. We are a public-private partnership between the Department of Defense, industry, and academia. We are a membership-based organization, and we really offer a number of benefits to our ecosystem, to folks that are members or partners of ours. We are a trusted advisor. We're not here to sell you a specific product or a specific solution. We are here to help you network and help you gain the best foothold you can as you look forward to transitioning to a smarter manufacturing future. We are a talent developer. As I mentioned, we are developing new venues, new tools, new teaching techniques to really make sure that the advanced manufacturing pipeline is robust and healthy going forward. We are a convener. That's what we're all doing here today. We are bringing the experts from around the country and around our ecosystem together to talk about how advanced manufacturing is moving towards a smarter future. We're a technology showcase. Pre-COVID, we had about 5,000 visitors a year to our Detroit facility, and encourage you to visit us when you can, when it is safe to do so. In the meantime, you can take a virtual tour of our facility on our website and poke around and see how we are bringing the art of the possible to reality, and all the pieces of machinery and equipment that we have available to connect the materials, processes, systems, and talent. We're actually due for a revision of our virtual tours. We've been evolving over the year during this pandemic, and so more to come on that as we head into 2021. We are a connector. Again, we're a public-private partnership bringing together the experts in their fields from each of those, government, industry, and academia, and we're really trying to move the needle in driving American manufacturing into the future. And finally, a technology accelerator. We want to move innovations from concept to commercialization as quickly as possible, so they can be addressed and adopted by industry as well as the warfighter. So I mentioned leading innovations for tomorrow. That is our technology program. Really falls under these 4 pillars. There's some more meat on the bones as it relates to those 4 pillars on this slide. As you can see, we focus on the digital, focus on smarter manufacturing, and go back into our history as an organization in our material science history with advanced alloy process development and multi-material joining. Again, all of those pillars really tackle the connecting of materials, processes, and systems. On the talent side of the equation, we have 4 really focus areas. We have Ignite, Mastering Manufacturing, which is our 3-year foundational curriculum that we've developed with the Department of Defense and have been offering it at our Learning Lab in Detroit. Again, pre-COVID, we had 100, 120 students in our facility each and every day taking part in that curriculum. In our Lift Learning Lab, which is made up of 7 specific labs. And we also offer world-class certification programs. CNC operations, welding, and robotics is coming online there as well. And finally, Operation Next, which we're very proud of, which is a program that we've developed. It started off as a program that was for separating military members 6 months before they left the service. We offered them the opportunity to earn some credentials in CNC machining, industrial technology maintenance, and welding. That began as a pilot program in 2018 at Fort Campbell, Kentucky. We have since expanded it. We just announced this week that we have expanded it to the Michigan National Guard and Reserve and their families. So we're excited to be able to provide that to our Michigan servicemen and women. We're looking to expand those to 8 additional facilities over the next 3 years, thanks to funding from the Department of Defense. We've also expanded it into industry. We were funded earlier this year through the CARES Act that was passed by Congress and signed by the President to expand Operation Next into industry. So we're providing training opportunities to 250 workers, particularly in small and medium-sized companies here in Detroit and Pittsburgh, to really help them try to recover from the pandemic that we've all been working through. So that is one of our most prized programs. So and we're happy to talk to anyone about that with more detail for sure. So with that, I want to thank you for taking time to join us today. Please follow us on LinkedIn and follow us on Twitter to stay up to date. You can visit us at our website, as I mentioned, lift.technology, and take our virtual tour. So with that, I will stop sharing my screen and hand the ball over to Robert Hurlston from Fidelis to talk a little bit about what they have going on. Robert, I'm stopping sharing my screen, so the floor is yours.
All right, can you guys hear me?
We can. And I can.
All right, perfect. And you can see the screen?
We can. Thank you so much.
All right, great. Okay, so first of all, I'd like to take a second to thank everyone for coming to this webinar today. It's unfortunate that this is all we seem to get now in terms of content from, in terms of conferences or anything like that. So we're all getting a bit more used to it, at least. We're really excited over here at Fidelis to become a part of LIFT, and hopefully we think this webinar might give you all a flavor of what we're about. Today we're going to be discussing our thoughts on the changing role of CAE in an increasingly virtual product development process. So a bit about the webinar content first of all. So we're going to talk a little bit about Fidelis, who we are, where we came from, etc. And then we're going to dive into why do we simulate, right? I know many of you might be experienced with simulation, many might not be. So it's always a good place to start. What's virtual product development comes next. And then some of the challenges, or the biggest challenges that we faced on a 2 or 3 year virtual development process that we just came off the back of. And so hopefully that can give some insight into where we need to work to get closer towards this truly virtual development model We're going to look at big data and virtual design of experiments. And then finally, I want to touch on the 3D experience platform and some of the advanced simulation roles within that. So first of all, an introduction to Fidelis. We are a provider of high-end CAE services, and we're also a reseller of Dassault Systèmes industry-leading CAE software. So rather than being, the typical churn and burn button pushers that you can find all over the world, we aim to be a little bit more focused and provide end-to-end simulation-based engineering services and turnkey software implementation with industry-leading support. We know there's a lot of cheap resources out there for CAE. That is not who we are. We believe that our strong leadership, technical expertise, but most importantly, unrivaled customer service make us a perfect choice for solving very complex engineering challenges. And we are located pretty close to Lift in Troy, Michigan, so about 20 minutes north of Detroit. This is our leadership team. So we'll start with myself on the left, Rob Hurlston. I am currently our chief engineer. Very seasoned analyst with about 20 years spanning many different industries and analysis methodologies. I am originally from Manchester, England. I have a PhD in nuclear materials engineering from the University of Manchester and also some management degrees as well. Next on the middle, we have Bill Webster, who's our Director of Engineering. He is a career analyst. He also has 20 or so years of experience at this point, an extensive CAE skill set, again, spanning many different industries. Bill's also a seasoned project manager, so he's been responsible for a number of multi-million-dollar product development projects in the recent past. So a good person to have on our team when we're talking about virtual product development. And then Ravi, who we have as more of a technical advisor at this point, 40 years of experience in the automotive industry dealing with CAE and managing very large teams. And so he gives us a lot of experience in that sense. We cover really the full gamut of industries. So anything that you can simulate with physics, we can really deal with. Obviously, being from Detroit, we deal a lot in automotive. We've done a lot of work with Boeing and Pratt & Whitney suppliers for the aerospace industry. We're also touching on the space industry as well with companies like Blue Origin and S&C. We've done many different projects in the industrial equipment realm, ranging from things like agricultural vessels to an animal feed mixer, all the way through to factory robotics. And not to labor too much on every industry that we've touched, we are ITAR certified, registered and compliant, should I say. And so that does allow us to deal with defense and government contracts too. So a little bit about what we offer. So first of all, we're a services company. We offer your typical CAE services, so structural and thermal analysis. I do have a specialism in fatigue and fracture, so that's something that we do specialize in. Explicit dynamic becomes a little bit more complex. And then where we really like to shine is in our methodology development and optimization capabilities, which is what we're going to be talking about more today. Our software offerings range from the 3D Experience platform, which, as I mentioned, I want to talk about a little bit more later on. We do also offer Dassault standalone CAE products, so that ranges from Abacus, which is the FEA solution. FE Safe can deal with durability. Tosca allows us to optimize shape and flow, and EyeSight is a process optimization software. We do provide industry-leading support, with all of our engineers also being Dassault certified support experts. So again, that feeds into our narrative of being a customer-centric business. So to get into the real crux of the presentation here, what are we talking about when we mentioned the shifting role of CAE in product development. Well, what we're really saying is we're moving from hardware-driven design more towards simulation-driven design. So traditional hardware-based product development methodologies are break, fix, repeat type methods where we are doing a lot of physical testing, we're doing a lot of prototyping, and it's very expensive and very time consuming. And typically CAE might fall in at the very end of the process as kind of more of a box to check. I think most of you on the call, if you're in the product development realm, might be more of a hybrid math-based product development method where we're looking at still physical testing driven design, but supported a lot more by simulation. So we are learning still from our simulations, but we are predominantly physically based. And what we all really want to get to, odds, is this kind of holy grail, is the virtual product development method where we design by simulation, we optimize by simulation, and we are continuously learning using simulation, and then finally maybe validating at the end with physical testing. Why do we want to do that? Well, simply put, it's cheaper and it's faster. So we can front load the problem solving part of the design process to the start rather than having it at the end when we've spent a lot of money prototyping and designing and basically designing off best practices. It eliminates trial and error engineering, and it reduces, again, as I said, development costs and time to market. We can reduce number of physical tests or maybe eradicate them altogether. We can eliminate unnecessary development cycles, so going round in circles where we're not really sure what's going on. And we can minimize quality issues that sometimes occur at the very end of the product development cycle once we think we've finished. So the virtual product development process still relies on having the right people in place. So this quote I always like is, it says, owning technologically advanced software is not the same thing as truly being technologically advanced. We can own all the software in the world, but if we don't have the right minds to pair it with, it's essentially useless and a black box. So this is where Fidelis gets to separate itself from the rest of the more traditional FEA suppliers in providing end-to-end virtual testing workflows. And what we need to do is understand the product development process properly, develop novel solutions to the unique engineering challenges that we face, and then importantly, package methodologies and results effectively so they can be used going forward. The rest of this presentation will be based loosely on a case study that Bill and I worked on over the last 2 or 3 years, and that was with a predominant tier 1 supplier of axles in the Detroit area, and we were tasked with developing CAE prediction methodologies for between 30 and 50 physical tests. The 2-year project was very successful. We reduced first-time quality occurrences significantly, and that allowed us to get it right first time, save millions of dollars in annual savings, and kind of put to bed this old-fashioned build, test, repeat type design strategy that was there previously. Before we go any further, it's useful to introduce the CAE Maturity Scale, or the idea of it. And what we're looking at here is a way to characterize how much faith we have in our CAE methodologies, starting at 0, where we say we just cannot simulate this at all. Level 1 might say, well, we've got some capability, but it's not really very useful. Level 2, we can sort using A to B comparisons. And then really where we're aiming to get towards is level 3, simulation predictive, but not without physical calibration or a lot of physical testing. And then 4 and 5 is where we want to be. It's predictive, confirmation testing may or may not even be required. So what were the challenges of going virtual? And with this being more of a philosophical discussion rather than technical, we thought it'd be useful to focus on our biggest non-technical challenge that we faced during our 2 or 3 years. And that was conveying trust in a virtual product development process. Typically, with traditional CAE, management might deal with the check in the box, as you will, at the end. They don't really see a huge amount of value in CAE. It's more of an afterthought. Designers might view it as kind of a nuisance where, well, you're telling me my design's not going to work, but I don't really believe the answer that you're giving. Project managers think it might be inaccurate. They've seen a lot of data and they've kind of seen the CAE and doesn't necessarily match up. And then testing engineers know it's inaccurate because they see the data every day. They just know that the CAE often does not match up with that. And there's a good reason for this. We'll take a look at it now. Traditional CAE will provide one single data point when we ask a question such as, how does this part or assembly perform? So I've got a little imaginary case study on the right-hand side here, and we're going to say, ask our CAE department, how many cycles will this differential case see before it breaks? So we run our CAE, and we say it's going to last 274,698 cycles. I can tell you now that you have more chance of winning the lottery than that being the correct answer to this question. Probably about 1 in 300,000 chance that this is the answer. In reality, of course, there's no single answer to this question. So from the lab or the field, this is more like what we see. On the right-hand side, again, I derived some physical test values of a fatigue test with the very advanced method of bashing the keyboard 6 times. But this is very representative of what we would see in real life. And of course, in real life, we have scatter from geometry, from material, forming processes, the assembly itself, and then even as far down as, well, are the testing engineers truly testing the same way every time? The answer to that is no. So we might have 6 parts here in fatigue, and we're getting results anywhere between 150,000 cycles and almost 450,000 cycles. The question is, which one of these answers is the correct answer? And the answer is all of them are, right? They all actually happened in our real components. And so now we're looking a little bit silly over here in the CAE department when we gave this single answer. Typically, our end customers will want to know what percentage of parts will fail in service. Usually that's in terms of reliability and confidence. Sometimes safety critical parts cannot fail at all. So something like a turbine blade, a wing, a wheel hub, etc., might have a requirement of 1 in 10 million probability of failure. We don't have that much data. We're never, ever going to have that much data. So we use statistical tools to characterize the behavior of a population with a small data set. And so you can see that on the right here, typical Weibull analysis. Many people will be familiar with it. We've got our reliability and our confidence in our prediction. Here's an example of what we might give for a typical automotive component. We might want a 10% failure rate with a 90% confidence. And so all of a sudden, our 150,000 cycle lowest test, all of a sudden now we're moving that down to maybe 100,000, or maybe if we want a 99% failure safety rate, we might move it down to 50 or 30,000. Now our 250,000 cycle prediction is starting to look worse and worse and worse. So how do we increase confidence in our predictions? So on the left-hand side, you can see we've got a plot of specimen number with cycles. And here's our CAE prediction. It is in error at 100,000+ cycles, so our worst performing test, and even more with our reliability and confidence built in. So we have 2 options, in our opinion, to fix this problem. And this is what we came up with during the program. Number 1, we can use big data. So we can use existing historical data to qualify and then subsequently bound our analytical predictions. Secondly, we can use design of experiment type methodologies, use the power of virtual testing to assess hundreds or even thousands of different samples very quickly and very easily. So what's big data? Well, really what we're saying it is in this context is many organizations having years or even decades worth of data just stored either in the back of a cabinet or in the bottom of a server. It can be field data, it can be pseudo field data. So there we're really thinking about test track and things like that. It can be lab data, it can be all kinds of different data. And so how can we make use of this existing data in our current CAE predictions? Well, first of all, we can use it to validate our methods. And so step one in this process is still to have a method. We still have to develop a method that we think can capture the physics at least acceptably. Secondly, we use it to correlate with the existing data. And so the more data we have, the better, obviously. And then finally, if we plot this on a log-log scale, we can visualize the prediction capability of our method and demonstrate relative predictive capability. So that might look something like this. If you have a poor or non-robust CAE method, we can see that the line of perfect prediction really is the red line, and we are nowhere near it. We've got sometimes we've predicted high and we've got low historical performance. Sometimes we're predicting really low and we've got very high historical performance. At this point, we would have to go back to the drawing board and improve our methodology. But once we have an acceptable methodology, our plots will look something more like this, where now we can say, well, all of our plots, all of our historical data is falling close to this line. And this can be data from many different, let's just say we're looking at an axle assembly. It can be from many different types of axles and many different years or even decades of end customer. Our method should be able to predict all of them. One thing we should note is that we do have to go back and build models of old parts and old assemblies, which can be time consuming, but it allows us to build this confidence within our CAE predictive capability. And that's what we need to do in order to go forward with truly virtual product development. Secondly, we can use our big data even further, and now we can use it to predict, actually. So we're using Weibel again, and we're going to build some prediction bounds by developing what we call a prediction ratio, which is virtual versus historical. One would be perfect correlation. For example, if I have a 80,000 cycle prediction, but reality was 100,000 cycles, our ratio will be 0.8. We then perform a Weibel analysis on this set of ratios and derive ratio bounds per our requirements. So then we end up with something that looks like this. We've bounded our data, and we have some scale factors that we've bounded our data by. What this then allows us to do is scale our CAE predictions accordingly and derive statistically derived or driven ranges of possible outcomes. And so previously we asked, how do we increase confidence in our predictions? We account for the test scatter. That was the missing piece in the puzzle. So now, instead of having a single value, if we take our example from previously of 270,000 or whatever it was cycles, we times it by a half, we now have 137,000 cycles. So we've bounded it on the lower end, and we have 500,000+ cycles on the higher end. And all of a sudden, our prediction capability looks a lot more convincing. Now we can go to management and say, we predicted accurately. The scatter is always going to be there. We need to understand how to predict it better. We've got data-driven statistical analysis, and even more importantly, we capture in effects of physics and tolerance that we either couldn't predict or we don't want to try and predict. So let's imagine a second phase particle was the cause of a fatigue initiation. We can't predict every single possible location of a second phase particle in a component. That would be literally impossible. This methodology allows us to capture unknown physics using historical data. We've now achieved level 4 or 5 maturity in our CAE method. But what do we do if we don't have data to begin with? So we can't expect every customer of ours to have just piles and piles of data laying around for us to use. If we remember, scatters caused by geometry, material, forming processes, all the things we talked about before, how can we generate our own scatter? And we can do this by knowledge and understanding of tolerance and physics effects on the final result. And we do this by design of experiment type design. We parameterize independent variables and then run many combinations of these known possibilities to come up with enforced scatter or analytical scatter. Response surfaces can be derived and can be plotted on this data and essentially give us an infinite number of tests or test results. CAE can then, again, bound our physical test results, and more importantly, we can understand the effect of different tolerances on our parts. So perhaps we might say, well, material had a huge impact. Let's improve our tolerance with material. Or having this fillet from 3 millimeters to 4 millimeters gave us a giant range of data. And so we can decide where we want to spend our focus in our design process. The requirements for a successful DOE are that we have, again, a robust model. We cannot get away from the fact that we need robust CAE methodologies. It's no use generating data for change in parameters if they don't reflect the real world effect of those parameters. Our changing in parameters has to be based on real world physics. Finally, we might want to utilize something like a Monte Carlo simulation with DOE, and that allows us to predict the statistical likelihood of performance based on some known statistical likelihoods of data coming off the line. If we want to do this, we obviously need to know from some sort of historical data what our statistical models are for each parameter, or else we simply can't do something like a Monte Carlo simulation. At this point, we think we should be towards this 95% accuracy of CAE, and we can slowly start to build in virtual product development methods. Our time to market and wasted spend can be significantly reduced with this get it right first time design methodology. Something else to note is we can also push boundaries that simply wouldn't have been economical previously. So things like using topology and shape optimized products rather than more traditional methods. We can look at using exotic materials and novel manufacturing methods, maybe like additive, more easily explored without the hefty prototyping and physical testing costs that we would have traditionally incurred. So a couple of examples of some of the work we did, just so that you know, we did do some work here. We looked at some high pressure die cast components. High pressure die casting allows us to rapidly produce quite complex shapes. In those complex shapes, we will always have many different stress concentrators. And fatigue prediction is extremely important in things like axle components. And so we have a myriad of challenges when it comes to high pressure die casting, things like porosity, flash, ejection defects, and what we're going to focus on here, stress gradient effects. Stress gradient is always associated with stress concentrations, and we can't get away from them. Essentially, every component we have will have some stress concentrations in it, and therefore will have some stress gradients associated with those. Stress gradients known to significantly affect fatigue life, and so if we ignore them, very often our fatigue predictions are very inaccurate. So we'll get low life, we'll get incorrect failure locations, and sometimes even incorrect mechanisms. There's a number of ways that we can fix this, typically special meshing, which is extremely time consuming and almost to the point where it's non-usable in a production setting. We can also purchase very expensive software that is almost designed just to deal with this problem. We didn't want to do either of those, so we developed some scripting ourselves to extract von Mises stress gradients from every node within our models. And then we use literature-based solutions to deal with the effect or the benefit of stress gradient on these nodes. What that really did is locally changed the EN curve, so the fatigue life curve for every node, and it allowed us to provide benefit where we have these stress gradients applicably. This was then packaged in a simple to use GUI, and you can see from the lower right image there, our correlation map is, if you believe it or not, very, very good compared to what we could do before. We were able to consistently match initiation location and fatigue life using this method. The second example I want to draw your attention to is predicting shaft failure. So case hardened shafts are used all the time in industry, whether we're using induction hardening like the picture on the right, or whether we're using carburizing methods. This gives us increased strength and fatigue life in our shafts. The problem is we have complex stress states associated with mating splines, and we also have added complexity because of our hardening method. So we have martensitic phase change on the surface, which gives us a hard and brittle to soft and ductile transition between the surface and the core of the shaft. So we were challenged with developing some new methodologies to deal with this in terms of both fatigue and ultimate torsion. What we ended up doing was actually casting aside our traditional FEA methods altogether and coming up with some closed form solutions to predict notoriously difficult behavior in shafts. As I mentioned before, we've got material discontinuity, we've got spline stress concentrations that are in themselves difficult to deal with, but when we've got spline rolling operations that don't necessarily match the CAD even, we essentially have now an impossible situation. Closed form solutions provided accurate and timely methods for prediction of both fatigue and fracture in these case hardened shafts. And in fact, we were able to take analysis times down from maybe hours or days to 5 minutes using some very novel mathematical based models. And you can see our correlation map there. Again, it's sanitized, but it's very, very impressive, especially compared to what we could do before. The plot on the bottom right is a load displacement curve, and not only could we match the behavior of the load displacement, we also got the failure location, the failure load and angle correct. I think it'd be remiss of us not to mention the 3D experience here, since it can help us massively use the ideas and the methodologies that we've just been talking about in real life settings. So what is the 3D experience? Well, Dassault calls it a business experience platform. And what this really means is it's a single source of truth-based PLM platform. When we say single source of truth, what we mean is rather than a traditional directory-based data structure, we go to a database data structure, meaning every single person in the organization is working from one single file, and they access it using metadata in the database. In real world terms, what that means is we are no longer checking out files to do analysis, checking them back in for the designer to go check them out, change them, etc. We are all working from a single file. That file can, when edited, can go and affect our simulations. So we are no longer passing work back and forth. We're all concurrently working, which can save tons and tons of time. The 3D experience is packaged by role and not by software. So if we have a designer, he might have the design package with the ability to do some simple simulation. The next guy might be a simulation engineer, and so he would have something more like a full FEA package, but he wouldn't necessarily need the design roles. And so we can really tailor our capabilities to our employees. It's socially collaborative, and it extends across all the disciplines within our organization. So what we mean there is, or what we are able to do, is break down typical silos within organizations and allow every stakeholder to have visibility throughout the whole process. So a marketing or a salesperson can see this design as it's coming along, they feel involved, and they don't feel separated from what's actually happening within the organization. Finally, it's designed for the cloud. And so what this is really doing is allowing small, medium businesses and new industries to take advantage of what they would previously have considered to be out of reach new technologies. This is what it looks like. It looks somewhat like a web browser. It's on the cloud, as I mentioned, or it can be. And really, the top left corner here with the widget, the compass, if you will, is where all the magic happens. And so we have the ability to quickly and easily flip between our information intelligence, so our PLM, our change management, etc. We've got our social and collaborative button at the top there, which is kind of like actually a Facebook or a social media platform. It lets all stakeholders be involved in the process all the way through. Of course, we've got our 3D modeling and simulation capabilities as well built in. And we're going to just talk briefly about some of the simulation capability within the 3D Experience platform. So what Dassault did in the mid 2010s is to take all of its industry-leading CAE capabilities and repackage it into the 3D Experience platform. So what we've got is the solutions we all know and love if we've used them before, just in a different setting. 3D Experience is powered by, as I said, best-in-class standalone solvers, Abacus for our FEA. It's got FE Safe built in for our durability analysis, Tosca and EyeSight for optimization, and it also includes the previously discontinued Abacus CFD solver, which is a Navier-Stokes-based fluid dynamics solver. Finally, we should mention the 3D Experience has some new roles for the new industries that are emerging around us right now. So we've got things like the additive manufacturing engineer, which allows designers to design specifically for additive manufacturing build-up and also thermomechanical behavior during printing. So things like warpage during cooling can all be included in these types of simulations. We're always using a lot more plastics every day. We can use the plastic injection engineer to simulate filling and packaging, warpage and mold cooling very early in the development process. So this avoids us coming up with these brilliant shapes that we're like, oh, we can't make them in the end. And then finally, the functional generative designer is really Tosca within the 3D Experience. It's allowing us to quickly and easily optimize use of our design spaces and improve some of our basic and not so basic parameters like stiffness and strength. It also allows us to quickly and efficiently compare designs that we've done and look at key features of those designs like weight, performance, cost, etc. So that brings us to the end of the Fidelis part of the presentation. I would like to thank you all for listening, and I think Joe might have some questions for us.
Yeah, sure. Thank you so much. Again, if you have questions, please please utilize the chat function. You can address them to me, Joe Steele, the organizer. Thank you so much, Robert, for the presentation. Everyone in the audience can see now why we appreciate you guys as a member, particularly connecting the digital to the physical and make things connect them so things can be produced and developed faster and cheaper. So we all appreciate that. Robert has his contact information up on the screen, so please reach out to him directly if you have any questions afterwards. But we do have some questions that came in via the chat function here. So, Robert, can you talk a little bit about the use of AI, and is it being used really to evaluate the large data sets that you're dealing with?
So AI is certainly in the early phases as far as we're concerned. We haven't had a ton of experience with truly AI, but I think it's certainly on the way. But yeah, I can't speak too much to it. In terms of the way we process the data that we were using in this particular example.
Okay. Where does field performance data fit into your entire process, including any warranty or reliability data by actual customers? Deal with field performance data at all?
Yeah, so we did have access to some field performance data, and essentially we paired that with road load data that we knew of and tried to bring back. We knew how many miles the car had done, so we could pair our known road load data to the expected experience of the components in the field. Fortunately, we didn't have too many field examples to use, but we did actually include some of them in the analyses that we were doing. So yes, we were able to do that.
Are you able to predict, talking about faster and cheaper, are you able to predict the reduction in time and the reduction in cost as it comes to some of these individual projects?
You know, we didn't get that far along, and we were certainly more involved in the prediction or the kind of physical prediction of behavior. So that would be more like kind of cost management and stuff like that, which I'm sure was done higher up the chain. We didn't have too much involvement in that. Maybe, I don't know, if you reach out to Bill, my business partner, he was more involved with project management side of that project. Mm-hmm. So maybe he could speak a little bit more to it, but I personally can't.
Sure. Again, contact information is on the screen here. And you reach out to those guys directly with some more specific questions. Have you done any? This goes back to our history at Lyft as a materials and metallic research. Have you done any modeling of friction welding and the processes involved there?
I've not actually used that, but I know Abacus is particularly, or I guess Smulia is particularly pushing towards those kind of novel joining methodologies. So no, unfortunately I haven't, but we certainly have the capability to do that. And I think one thing that we should kind of keep in mind is that all of these methodologies will be in some way developing along the way, right? And as long as we have methods to capture physics, we can do this kind of stuff with these new multi-physics solutions that are coming out from Dassault and other software manufacturers.
Yeah, we obviously have a lot of members that are involved in the welding and joining processes, and as you know, at Lyft, we have we give a plug to our world's largest linear friction welder that we have on site facility. So
one of my buddies when I was doing my PhD was actually doing a whole PhD in friction welding. So I'm pretty familiar with it. I just never have tried to solve for it.
Yeah, and it's noted that TWI, the Welding Institute from over in the UK, is one of our partners as well, and can certainly help with friction welding modeling as well. So maybe we can connect the two of you to talk about
Yeah,
that.
I actually have pretty decent connections there since the University of Manchester was heavily involved with TWI. So yeah, I know quite a few of the people. In fact, the guy who examined my PhD defense was from TWI.
All right. Well, there you
Yeah.
go.
There you go. Small world.
Yeah. And I don't mean to, I don't want to start a fight, but Manchester United or Manchester City?
I'm United. That's why Fidelis is red.
That's why Fidelis is red. Fantastic. Fantastic. Well, we appreciate the presentation, appreciate your membership. I will ask one more time if there's any additional questions out there, please feed them into the chat. We have a few more minutes left, but I do want to be respectful of everyone's time today. Again, the contact information is on the screen there. So please reach out to Robert and Bill. And next time you're in the Detroit area, you can come visit Lyft and then stop by and see Fidelis as well, or meet him at our facility to talk about your next project or talk about how they can help you moving forward. So when it's safe to do so, of course. So I think that might be it for the questions, Robert. So thank you for the presentation. Thank you to everyone for joining today. Certainly appreciate it. And hopefully everyone stays safe and healthy out there as we end out 2020 and move into 2021. So thank you very much, everyone. Hope you have a great rest of the day.
Thanks, guys. We really appreciate it over at Fidelis.
Thank you.